So welcome everybody. I'm delighted to kick off a new session as a part of our Arab molecular simulation community, and I hope we can achieve something great together. So it is an absolute pleasure to introduce our distinguished speaker for today, Professor Oliver Kühn. He's of course, like I would introduce as well-known scientist in the field of theoretical and computational physics and chemistry, with a particular focus on photophysics and chemistry, so we can say like light-matter interaction. So Oliver started his academic career or his academic journey at Humboldt University in Berlin, where he studied physics. And in 1990, he obtained his diploma in physics, and 1995, he obtained his PhD in theoretical physics from the same institution. Later, he did like 2 postdocs in the United States and Sweden, and in 2000, he obtained his habilitation in theoretical chemistry at Freie University, Berlin, under the guidance of Professor Jörn Mans. In 2008, he was appointed as a professor of theoretical physics at the University of Rostock, which I am working, of course, under his like guidance. Like a group leader with him. Oliver Kühn visited like different institutions in the United States, Japan, and Russia, and he made like significant contributions in Egypt, particularly at Cairo University. Today, he is going to talk about photophysics of iron complexes and give like a theoretical challenge. So please join me to welcome Oliver Kühn, and please, so the floor is yours.
Okay, thanks a lot. And yeah, thanks for this nice introduction and for setting up this this meeting. I think that's going to be a great opportunity to exchange ideas and communicate scientific results. So today I will talk about essentially density functional theory, and with a particular focus on challenges which appear if you look at iron complexes and the photophysics and also photochemistry of iron complexes. Okay, so before I start, let me just thank those people who essentially did most of the work, which is Sergei Bogarev, who also will give a seminar in this series, and Olga Bokareva, who did her habilitation with this topic, or will do. She's not finished yet. Financing comes from different sources. Most notably these days is the German Science Foundation, and here are our experimental collaborators from Rostock, Paderborn, Mainz, and our theoretical collaborator from Vienna, Leticia Gonzalez, and her group, most notably Patrick Zobel. All right. So here it started. So some time ago, we had a grant to study the photocatalytic water splitting, or essentially a half reaction, and based on a photosensitizer, which you see down here. So it has as a metal iridium. All right. So then we studied basically the whole series of complexes separately, like the excitation, basically the electron transfer from the sacrificial reductant, and then the fate of the reduced species, which basically donates an electron to an iron-based catalyst, which eventually like sets free hydrogen. We also studied what happens if you increase or modify the absorption properties by just adding like a small silver clusters, and so on. So this was in a way rather successful, and well, also in terms of experiments as a proof of principle. So there's one thing in terms of theoretical challenges, which is related to the fact that you have different charge transfer states. So let's see, we plot here the potential curve. Well, it could be any coordinate, it doesn't really matter at this point. And you see what you start from the electronic ground state to one of the excited states. So various processes happen. In general, you have a kind of heavy metals, you have intersystem crossing from the singlet to the triplet manifold. And you have internal conversion due to non-adiabatic coupling, that is the breakdown of the Born-Oppenheimer approximation. And so this all brings you back, say, for instance, from the initially excited state to some, say, metal to ligand charge transfer state. Well, and with this charged separated states, you could either have photoluminescence, or you do, as I mentioned before, like this electron transfer with this sacrificial reductant. And well, with this, then you can go like do further reactions, as I mentioned before, like the electron transfer to the iron-based catalyst. All right, so what's difficult now if you want to describe this? So there, as I said, there are several charge transfer processes. Intramolecular, so you have a charge separation from the metal to the ligand, and intermolecular from like one well, species like the photosensitizer to the sacrificial reductant. So this is basically the challenge we face here. And of course, you have to kind of make some predictions for these processes. You have to be very accurate because it gives you some sort of constraints of thermodynamic or kinetic nature, which tell you how to effectively make use of these charge separated states. Okay, so then you think of calculations, basically to get some mechanistic understanding of the properties or the what happens after excitation by a photon. You would think of, okay, let's just solve the electronic Schrödinger equation, well, which you all learn in the physical chemistry course. And well, what you have here, you have the kinetic energy, you have the electron-electron interaction, and you have the electron interacting with the nuclei, which are, of course, positively charged. All right, so and if you solve this, then you well basically get all information you ever could have, and predict properties, predict experiments. The problem is that you have here the electronic coordinates, and you have n electrons, so you have 3n coordinates. Just imagine you do this basically by discretization on a numerical or discretization of the coordinate. Say you take 10 points per coordinate, and then you have 3n dimensions, so you have 10 to the 3n points you would have to calculate or you have to consider in order to solve this equation. Well, this becomes very rapidly totally inconceivable. Okay, so what's the alternative? And the alternative is density functional theory. There are these famous Hohenberg-Kohn theorems from the 1960s, which in a nutshell give the recipe how we can equivalently or describe the properties of the molecule in terms of the electron density. All right, so that's the electron density at position x, and here you kind of integrate it over all the other coordinates. So it's much simpler. You have just 3 coordinates. So that will be dimension 10 to the 3 if you go and do it on a calculation on a lattice. Well, that's easily doable with nowadays computers. In practice, what you do is you don't do this on in that way, but you can show that there's something called Kohn-Sham equations, which give you the Kohn-Sham orbitals phi j, and like their energies, which is kind of molecular, can be seen as molecular orbitals, and which taken together then give you a representation of the electron density. And you sum here over all occupied orbitals. The tricky point, this is an exact prescription. The tricky point is this Kohn-Sham potential here, which contains the electronuclear repulsion, which comes from over here, and which contains the electron density. I mean, that's basically Coulomb interaction, which comes in here. And then comes the most tricky part, which is this exchange correlation potential, which derives from an exchange correlation energy depending on the density. Well, and that's kind of functional derivatives, never mind. The point is, in this derivation, one has kind of put everything one does not know, and whenever an obstacle occurred, it was put into this exchange correlation part. Right? So provided one would know this exchange correlation part, one would be in game and solve the problem of this 3n dimensional wave function, or in this case, a 3-dimensional electron density exactly. Of course, that would be too good to be true, and there are only approximate functionals, so the exact form of this functional is not known. And some of the approximate functionals you might, of course, know. This PBE or B3-lib is very popular, and so on. There are virtually hundreds, if not thousands, of different functions. All right. So what's then the next step? So that gives you the ground state, the electronic ground state, like the density of the electronic system in the electronic ground state. Of course, if we want to study photochemistry, photophysics, we also have to look at excitations. So there are different types of excitations. Say here you have like different parts. Say that's a metal center, that's the ligand orbitals, and here you would have local transition, which would be in that context a metal center transition. But you also have charge transfer transition, right? So from the donor to the acceptor, like metal to ligand charge transfer transitions, and that's a problem because the way you calculate now the optical or the electronic excitation is what's known as linear response time-dependent DFT. And well, when you derive this, there's something it's called Casida equations, which look like so. Basically, that's a generalized eigenvalue problem which you have to solve to get the excitations. All right, so I don't want to go into detail here, just mention the point. Because you have here these two electron integrals, like here and here, and you see here, okay, I is a occupied orbital, A is a virtual orbital, J is occupied, B is virtual, and you see here now you have I, A, okay, this is basically at site R1 or at the R1, and you have J here and B at R2. Right, and if J and so if you have a charge transfer transition, like these two orbitals will be kind of centered very far from each other. So basically, that the overlap are whoops, comes to my computer. So the overlap is 0, and so basically these terms do not contribute. And you get the excitation energy just as the difference in the single particle Kohn-Sham energies. And they could be arbitrarily wrong. And so you have different issues which come along with this. You have a wrong asymptotic behavior of the densities, so it falls off not with the proper dependence. You have so-called self-interaction error. You have in the fact that the HOMO-LUMO gap is not the difference between the ionization potential and the electron affinity. And then if you look at how charge-separated states are, well, their energy depends on the distance between, say, donor-acceptor, you would expect from the Coulomb's law something like 1 over the distance, and that's not fulfilled here. All because, like this, basically these terms are canceled each other. Of course, there's a remedy for that, and that's like these so-called hybrid functionals, like this famous B3-lib. So what one does here is one artificially adds some term which is coming here with a factor, which is called CHF. HF stands for hard to fuck. And essentially, what one has then, when one adds here something which is has the form of the exact exchange integral for Hartree-Fock theory. It's completely, if you want, like just to cure a shortcoming of this functional, because if you of these functionals, if you now look at this integral, you see here you have I, J being at the same, well, having the same electron coordinate, and AB as well. So what happens then is that for these charge-separated states, so these terms still vanish from the equation, but you have then basically this exact exchange. Right? So basically you get the right, in a way, asymptotic or the right dependence of charge separated states, say as a function of the donor acceptor distance. Right? But that's really a little bit ad hoc. And well, now, well, as I said, like B3lib is one variant of this. And essentially, these different functionals, so that's basically like the four different like two singlet and two triplet excitations of charge transfer character here for this iridium complex. And that's the transition energy, and that's basically different methods. And you see, like, depending on like all these different, like B-lib, B3lib, MO6, and so on, they differ in the amount of exact exchange you have artificially added to this. In a way, the C factor, which I gave in the previous slide. Right, and you see, okay, here on that side are more high-level calculations like CAS-FCF and CAS-PD2, but you see essentially when you take them as a reference, you can get, well, arbitrary results, right? So basically the energies shift wildly back and forth. So that's very complicated and not very nice to be predicted. All right. Okay. So when you then look at the absorption spectrum of these species for these different functionals, you see, okay, it's not only, I mean, this is here for one state, but you see also they have rather different absorption spectra. And that's, of course, making life very difficult. Okay. What you can do to improve on that, you can use the so-called optimally tuned range-separated hybrid functions. So in a way, what you do is for this sort of, well, you have local transitions and long-range charge transfer transitions, you add up for the long-range part, or you add up this kind of Hartree-Fock exchange for the long-range part, and for the short-range part, say for small electron distances, you use your whatever you had as the functional before. All right, but how you decide on long and short range, right? And you do this in the following way, that you say, okay, well, this is the electron-electron interaction here, and then you add basically you add a zero here, right? You see this cancel, but you say, okay, this part defines short range, this part defines long range, and this is the error function, and you see how this depends now on this parameter omega, which basically can be used, can be used to tune like what's long range and what's short range, right? So it tunes a fraction of this exact Fock exchange or Fock exchange, and the fraction towards between this one and the short range, say GGA function. Okay, but so what? If I now take like different values of that, so that's this omega, which is basically like the steepness of the switching function. You see that for this system, I get like different spectra. So apparently now I shifted the problem to finding an optimal omega. Okay, what's the rational way of doing so? Of course, like some of the parameters like the 0.33 and 47, they have been obtained by just like in a statistical way by looking at many different complexes and comparing with more accurate data and finding a compromise for this parameter. Okay, but where's the 0.18 from? And in fact, you can, there's a non-empirical way of tuning this range separation parameter. Right? So if it works as follows. So you have an energy of a charge transfer state. So it has the ionization potential of the donor minus the electron affinity of the acceptor, minus this Coulomb interaction 1 over distance between donor and acceptor. Right? So you have donor and acceptor. In exact Kohn-Sham theory, the energy of the HOMO, right? So this conjunct orbital of the n-electron system should be equal to the ionization potential. That's an interesting result, right? So that's exact, should be exactly true. What's the ionization potential is basically the difference between the energy of the n-1 electron system minus the n-electron system. So then you can just add one electron, then you get the energy of the HOMO is like the electron affinity, and this is IP of n plus 1, so it's E of n minus E of n plus 1. Well, it's important because you now can say, okay, if this should be true for the exact functional, why don't we enforce this? Right? So why don't we say, okay, I take a calculation and compare the ionization potential, which I get just from this difference here. So I do a calculation for the n-1 electron system and for the energy of the n-electron system, just take the difference, compare with the HOMO energy, and get this expression, and I do the same for all this electron affinity term. Right, and this gives me a function, or I can kind of average this in a way. It gives me a function called j of omega of this range separation parameter, and then I just argue that, okay, if I minimize this function, I get the best possible omega, which in a best possible sense fulfills these exact quantum theory constraint. Right? So basically, I construct a system-specific functional which fulfills certain exact properties. Well, remember, we don't know the exact functional, but here I can just say, okay, well, look, I just choose this functional to at least fulfill one known exact property. All right, so how does this work? When you, like, this is here for this iridium photosensitizer, you see again, so that's basically this J function as a function of this omega. And you see here, okay, well, if you're lucky, then this function has a minimum, and which then gives the best possible value of omega for your particular system. Okay, this one, the blue one, and the red one are the standard values, which are in whatever Gaussian and other codes fixed. And you see you get quite some differences here for this particular system. Like in particular, you get like the optimal value here is 0.80. All right. You can also work, let me just skip over this. You can also do this with salvation, which has some interesting points. And we did a lot of work on that. I just mentioned some of the papers we wrote in this respect. And I just want to show some results for this photocatalytic water splitting half cycle for this iridium photosensitizer. So it's about the quenching of the fluorescence of the excited iridium photosensitizer due to the reaction with the iron with the sacrificial reductor, right? And you see, okay, what you can see from this value, so that's kind of the photoluminescence intensity as a function of time. And you see here 2 decays, say if you have basically the bare photosensitizer where the no TAA is in, it has a very long decay time. And if you add a little bit of this sacrificial reductant, which then leads to electron transfer and therefore quenches the photoluminescence, you see a much more rapid decay. Actually, one can estimate, I mean, it's a bimolecular reaction, and one can estimate what should be the kind of diffusion limited rate. And it turns out that the diffusion rate is much faster than the rate of the reaction. So the quenching efficiency is very low. Why this is the case? I mean, we looked at this, and in a way that, okay, so you study the electron transfer between these two species, with this range optimal tuned range separated functionals in a way to how this has been done is basically you have the iron iridium photosensitizer here, and you move this TA around this and then check where basically it's energetically favorable to do the reaction. And when you do this, you find here that, okay, that's basically like the solid angles here. And what you see here is essentially the color-coded the binding energy. And these dots here is like those energies where it's energetically, or those angles where it's energetically favorable to do the reaction. And it turns out that it doesn't really come together. So basically, there are only few sites for good binding, and for those sites, it's not optimal for charge transfer. So the system is, I mean, in a way, not once it forms an encounter complex, it's not really optimal for charge transfer, which kind of explains the low yield. Okay, but I wanted, I mean, the title of the talk is about iron complexes. And so, I mean, iridium is nice, everything works. Also, you can go to ruthenium and so on. So it's all very nice. But of course, one would like to have, just in terms of sustainability, to have these reactions working, or these complexes working for earth abundant metals like iron. And there's all priority program, like controlled reactivity of metal complexes. So what's the issue? Why iron is so complicated? And some of you, or I'm sure you know, these Tanave-Sugano diagrams are for the D6 system. And it turns out that, well, in our iron complexes, right? So you have like ruthenium here, you have the position of the MLCT states, you have iron here, so that's basically where it crosses, it's the metal-centered states. And you see when you take ruthenium and compare to iron, you see that the following happens: that the metal-centered states are energetically below the MLCT states. So what then happens is you have like a cascade of events which lead to a very rapid deactivation and a short lifetime of this MLCT states. And that's, of course, well, hinders, if you say like this, you use this MLCT state to, well, as a kind of reservoir, a kind of a state which interacts with other species to have electron transfer and so on. So for that purpose, you would like to have a long-lived MLCT state. Okay, but well, that's basically in this iridium, like this MC states is way up in energy, so it's really everything can be stored forever, I mean, for nanoseconds in these MLCT states, but in iron complexes, that's not the case. So there's quite some active research going on to find long-lived MLCT states, and quite some progress has been made. Here we are also made a contribution to investigate a particular system and use what is called two-parameter tuning. Remember, I used this parameter omega to tune our the contribution of exact exchange and our approximate exchange, like for long and for short distances. There's a next, I mean, higher level of this when you not only use one parameter tuning, but two parameter tuning. Okay, say it's probably better to look at this lower part of the slide. So you have like B3 lip, that's a distance between electrons, and B3 lip, it's kind of hard coded, right? So you've always 20% exact exchange. In this LC B-lip, which I talked about before, well, it's with increasing distance, the Hartree-Fock exact exchange, the amount of it increases up to 100%. Now with this two-parameter tuning, you can, in addition, for short distances, mix in some exact exchange from Hartree-Fock theorem. which of course gives you more flexibility. Okay, let's see how this works. I mean, first of all, I have to tell you where do I get the other parameters from, right? So I give more flexibility, but I also need more constraints. So you could, of course, look at the fundamental homo-lumo gap, could have look at ground stability of ground state solutions, look at what's called delocalization error. So, and of course, also the experiment, right? So in terms of this delocalization error, there's another exact point of quantum theory, which is called Janak's theorem, that basically if you allow for fractional electron occupations, then between the n electron energy and n-1 electron energy, there should be a linear dependence on the fractional electron number. And so if you have a deviation from this linearity, it tells you, okay, well, this it can be related to the wave function being either too localized or too delocalized. Okay, in short, we have another exact property where we can tune the parameter, in this case, alpha. All right. Let's just look for these different, I mean, this was one set of different iron complexes I just show you. So it's basically all these carbene with these carbene ligands here. And you see you have like different substitutions. So you have like a series of compounds which have slightly different properties, which can be compared. What you see here is then, first of all, like this omega, and for this range separation parameter, you see it's always kind of like in the same range, which just tells you, okay, well, this range separation parameter, I mean, it's about the electron-electron distance. And say if you have like systems which have a kind of similar size, these typical distances will be kind of similar, so you wouldn't expect vastly different omegas here. Okay, that's fine. And what you then see here, basically in this plot for this IC1 complex, you see how this deviation from linearity behaves as a function of the fraction of the delta n, so the fraction of electron fraction, fractional occupation or fractional electron charge. And you see, okay, well, they all like, okay, so it always looks like so. It's not really huge differences. So basically, if you take like different pairs of alpha and omega, they behave rather similar. So it's not really a very strict confirmation of any or preference for any of these values. Right? If you look at this for like a two-dimensional plot, alpha and omega, you see this here in color scale. And you see there's kind of valley of optimal values of or optimal omega alpha pairs, and yeah, so it's really, there's some flexibility. So it's not really that one alpha omega will stick out; they will behave kind of similar. All right, but in general, one can argue that these parameters are comparable for a class of molecules. Okay. Well, do they all give, say now we have these optimal values, which are given here, like alpha omega pairs, or omega alpha pairs, and do they give good spectra? Well, you see here the experimental spectrum and the theoretical spectrum in blue, and you see, well, it's not really uniformly improving, right? So basically, you might argue, well, there's no systematic trend. And that's a bit a difficult story. I mean, in a way, you see already here, there are really many transitions. And what you did is, by tuning this omega, in a way, you kind of worked on the homo-lumo gap. Why all these other states should behave, I mean, why this omega alpha pair you get should be optimal for all these transitions. It's not that obvious. Okay, so in order to cope with this, we said, okay, well, let's set out for one particular system and study this with kind of all different methods and information we had at hand. It's basically, let's call it just CPMP. It's basically the same type of system, the same type of ligands as we had before, and it has been just synthesized and published last year. And we also did this alpha omega tuning for this system. Right, you see here, okay, that's alpha omega, and you see, okay, well, I get like this valley of alpha omega values, which are more or less optimal, in particular in this lower part here for this compound. If you ask yourself, I mean, how do the properties depend on this alpha omega? That's kind of interesting. You see here the position of the lowest MLCT single transition energetically. Right, in wave numbers, in wavelengths, in nanometers. And you see here omega alpha, and you see basically being on that range, you can get anything from whatever, 700 nanometer to down to 450 nanometers. Right, so basically these MLCT states are really, really very dependent on these alpha omega pairs. All right, how about the spectrum? And in fact, this system was nice to us because it gave a very good, very fair comparison with the experimental data. So basically, you see here this alpha omega optimization. That's basically the electron difference density for the lowest charge transfer transition. Right? So it looks very good. Definitely, it looks better as compared to this B3 look results, although it's also quite fair. Okay, but that's not all. In particular, the question is, well, okay, while we work pretty much on this, getting good values for these MLCT transitions, how about the other set transitions, these MC transitions, right? So I told you that the whole point of designing this or synthesizing these systems with different ligands is to change the relative position of metal-centered and MLCT states. Right, so you could also ask, okay, what happens here if I want to optimize for like an MC state? Do I get other parameters? And so we kind of looked at different ways of optimizing transitions. I don't want to go into detail here, just focus on this plot here. Right, so this white line was like the one which I discussed before, and these different other lines are like different other variants of tuning. And you see, it's all like in this range of alpha and omega, so it's really not which are in that value. So it doesn't really give you much news here. So well, presumably you don't get vastly different values for these tuning parameters if you go from an MLCT to an MC state. All right. Okay, so then what we can do? We could also say, right, these complexes are very big, right? But when so far we compare to experiments and like, so the absorption spectrum, I told you these are like many states, many transitions. So it might not be, and it's also not very highly resolved, so it might not be the best thing to compare with. So let's compare with exact calculation, or presumably exact calculation, which would be as a standard, this CAS-SCF, CAS-PT2 calculation. Of course, this has a problem that the system is far too big to go and really make a one-to-one comparison between many transitions. Well, so therefore, we did this only for lowest MC and MLCT states, and to try to design this CAS-SCF calculation just to get good values for these two types of transition. Okay, so let's look at this. And what you see here is the following. You get here, you move along this valley of optimal alpha omega. It's only alpha shown here, to make the figure not too complicated, but for each alpha, there's the optimal omega there. These are the singles. And so you see how the red curve is the MLCT position of the MLCT state, the lowest one, and the blue curve is the position of the MC state. Right, and you see, okay, well, look, if I now go from along this valley, I even changed the order of these two states. Okay, and I can also go for the triplets, and also I see, well, that's basically here the right figure, and I also see, okay, well, I changed the order of the states here at some point. Now look at the other points, right? So basically here, these straight lines are the cuspt2 values, and like the other points is like different tuning recipes. The point is that, and that's a very important message, is that these are not pure states. It's not really like 100% MC or MLCT states for most of the time. And what you see here down and up there, okay, I mean, MLCT is pretty good, but the MC states are mostly mixed. So they always have a kind of a mixture of MLCT character and MC states. So this might be the reason why the tuning parameters are kind of similar, but also this makes life rather kind of complicated, because you don't get really clear results and wouldn't be able to, I mean, as you see, if you compare with this cuspt2 here, you never really get a gap between MC and MLCT, which is exactly, I mean, at least not for those points here, exactly the one for you have this tuning. So you have to do a compromise. In particular, I mean, you want to have like the singlets and the triplets, right? So it doesn't come together. So you can do a compromise. And here we took like those points here at 0.2, which alpha 0.2. So it's basically here where the order of the singlet and triplet MC and MLCT transitions is at least correct. Okay, so then we have like two sets of parameters. One is here from this comparison of this range separated functional with cuspt2, and the other one is like from this optimal tuning, right? So this was 0.14. Okay, does this make any difference now? We want to compare these two sets of parameters in respect to the performance. Okay, so you can go, well, of course, you know this person, Ahmed Sivil, and you can go for RC experiment and do pump-probe spectroscopy. So which is essentially, in a nutshell, you have a pump pulse and you have a probe pulse, you focus it on your sample, and you have a time delay between pump and probe, and this then you use to, first of all, the pump triggers a reaction or an excitation, and the probe then at a certain time delay after the pump looks essentially what happened in between, right? And so you do this in terms of spectral changes. It's also called transient absorption. So what you then get typically is this type of signals. So okay, here is, it's like just a chromophore, doesn't really matter in detail. So you have like the absorption spectrum, the fluorescence spectrum here. It's excitation at a certain wavelengths, and then you see, okay, well, three contributions to the signal. So you have like, first of all, you bleach the ground state just because you excited some of the species. You might have stimulated emission in the range of where the fluorescence spectrum is. So these two are shown here. And then you have excited state absorption, which has a different sign, right? Because it's extra absorption. Okay, and this can be used now as if you just record this spectra as a function of the delay time between pump and probe, you can learn something about what's going on in the molecule. Okay, so here's like one of these complexes which I showed you initially, IC3. So that's typically how these spectra look like. One has to get used to read them, but just tell you that, okay, well, if you have this part here, which comes from our ground state bleaching, stimulated emission, and then you have excited state absorption. And this excited state absorption is actually telling you, okay, there's you have populated MLCT states, right? So that's known, that has been investigated. So I just mentioned this here. Right, and then you record the spectrum as a function of time, of delay time. You see basically at very long delay time, you back to almost back to well, that you have no spectral changes. Basically, the system is returned to the ground state. And then you can do some analysis of these traces and get some timescales. Right? So you get this so-called decay associated spectra, and then you get timescales for the process, and you have then to work on get the processes for these timescales. Okay, well, if you look at now to our CPMP ligand, you see, okay, well, it looks, well, compared to that one, it looks kind of not so interesting because like all the changes are just in the ground state bleaching simulated emission peak, and there seems to be no excited state absorption in that spectral region. So then you would say, okay, there should be no long-lived MLCT states. Okay. Now, how to relate this now to our calculation? So let's first see what the absorption spectra. Well, we already looked at this. So absorption spectra are not very telling here. So it's basically looking the same way depending on, I mean, independent on what sort of parameters you use. Okay, I will want to focus on dynamics, right? Dynamics after photoexcitation. And for this, we need potential surfaces. Right? So basically, this is a potential surface cut along a breathing mode of the Fe nitrogen distance. It's about 200 centimeter in frequency. All right, so you see here the triplet states and the single states in blue, in red and blue respectively. And then you also see these triplet MC state, which is, well, you see, okay, that's the MC state. That's the parameter set for the ground state calculation. Well, it looks like, put it like this, it looks like spaghetti in first place. But if you look at this closer, you see, for instance, that in this CASPT2 derived parameter set, the MC states are below the MLCT states, right? Energetically. So it's basically like this triplet MC here, and this triplet MC is over there. Which would mean that there's no, I mean, you would expect there's no long-lived MLCT states in the right-hand side case, and here there could be because the triplet states are higher. All right. Now, well, why there a transition at all? Well, I mean, you have non-adiabatic coupling. So basically, if you look at this curve, well, it looks nice, but well, it's complicated, but it even gets more complicated because you have not only spin-orbit coupling between the singlet state, the blue one, and the red triplet states, but you also have the breakdown of the Born approximation. Right? So basically, you have, and this is just a one-dimensional cut of this 3n minus 6-dimensional potential surface. And if I just take another mode, say, well, what you see here, this cut is so-called tuning mode. Right? So if you look at, go here, okay, you have this state, it's kind of crossing here. Well, that could be any of these pairs of states which you see here over here on the left-hand side. But then you have coupling modes, which normally lead to, well, if you move along these coupling modes, reduce the symmetry of the molecule. And then, well, if you take into this account this coupling mode, you see you get, well, let's zoom in here, you get these kind of photochemical funnels, these conical intersections, which just tell you that you have a very rapid dynamics, or can have very rapid dynamics, say, starting on this higher state and then ending up in this lower state here. Right? So that's a punchline. This picture is much too simple. Just gives you an idea about the relative position in an overall picture, but in order to really appreciate what's going on, you need to take into account other coordinates, notably these coupling coordinates, and then this will give you very rapid processes. And that's well known. In order to investigate this now, we teamed up with the group of Leticia Gonzalez from Vienna, and they did surface hopping simulation, which is essentially like a non-adiabatic dynamics simulation to find out whether the two parameter sets the one derived from the ground state calculation and one derived from the CASPT2 calculation lead to different dynamics. Okay, I mean, my time is running out, so I don't want to go too much into detail. But so what you see here is always comparison population of the ground state set, that's A, and the population of the CASPT2 sets, that's B. And well, that's adiabatic populations. That's a diabetic population. It's probably easier to understand. What you see here is essentially that you have a large population of triplet MLCT states for this first parameter set from the ground state. So that would mean that you trap the system in a triplet MLCT state, and well, which comes along with little change in geometry. And whereas for this other parameter set, you have a very rapid depopulation, and you go back to the ground state. So you have no transient triplet population for, I mean, trapping in a triplet MLCT population. And that's essentially in accord with experiment, right? Which did not, remember, we didn't find excited data absorption, so there's no long-lived MLCT population. And therefore, like, we would be in favor, by comparison with these simulations with experiment, it would be in favor to use this CASPT2 derived parameter set. One can go like more into detail, analyze different bond lengths and so on. So you really have like large bond elongations here for this CASPT2 set, which is a blue curve with respect to the equilibrium or the Frank-Condon geometry value. And you don't have so much geometry change if you look at the ground state derived parameter set. So, well, that's all in the court. Essentially, I try to summarize what happens in this kind of cartoon. It's really a cartoon because you might have noticed that we did not take into account the quintet stage, which is kind of tricky computationally. So what happens is that you make an excitation, and then really the MC state is below energetically the MLCT state. And so the system goes over here to this blue state, might be trapped, and that's also evidence from experiments, in this quintet MC state, and then returns back to the ground state. Yeah, to be continued, put it like this. So to sum up, let me just make a few points. What I try to convince you is that this functional tuning is an efficient way to obtaining a system-specific density function, and which is system-specific in that it, for this particular system fulfills certain conditions which should be true for exact constant theory. So it's not like an arbitrary functional which from the shelf. So it's a functional just for your particular system. That's good. There are many applications, and I think it's mostly standard to use this functional tuning nowadays, and well, including small molecules, even to solid state materials, and yeah, also our work on iridium photosensitizer, where it shows really considerable improvement with respect to performance, so if you compare to off-the-shelf standard functions. However, going to this earth-abundant elements like iron is kind of tricky, because there you have like this mixture of transitions of different characters like MC and MLCT, which, I mean, are at the heart of the photophysics of these complexes, and which cannot really, I mean, addressed in a simple way, in that sense that you can just use this OT, optimal tuned range separated hybrid functional, as a black box, and just get some parameters and then you're done. Right? We have seen that, okay, you can do very well for absorption spectra, but then for the dynamics, which is not visible in the absorption spectrum, you might be very wrong. Right? So therefore, you need some additional input from experiment or higher level calculation to really find optimum parameters. Okay, and with this, I'm finished, and just thank my co-workers, and which actually did the work, Olga in particular, Olga, and also Sergey, and our experimental co-workers. And yeah, thank you for your attention, and I look forward to your questions.